Picture a wrench, not a complicated tool, just a wrench. The kind a worker picks up 100 times a day on an oil platform, deep in the Gulf of Mexico, surrounded by pressurized gas lines and petroleum vapor so thick you can smell it. Now picture what happens if that wrench strikes a pipe and throws a spark. One spark, that's all it takes. The vapor ignites, the platform goes. Everyone in that section, gone. So the wrench cannot be steel, it cannot be iron. It has to be something that physically cannot produce a spark on impact, no matter how hard, no matter how fast. And it also has to be strong enough to actually work. Soft metals don't cut it on an oil rig. That wrench, used every day in one of the most hazardous industrial environments on Earth, is made from a metal most people have never heard of: beryllium copper. It is comparable in strength to high-grade steels. It still conducts electricity. It cannot spark. It's inside satellites, fighter jet instruments, and quite possibly the device you're holding right now. For decades, engineers who spent their careers in materials science used a specific phrase when they talked about it: there is no substitute that does everything. Here's what they don't put in the brochure. The workers manufacturing it, the machinists running the lathes, breathing the air in those factories, were developing an incurable lung disease. Not the people using it, the people making it. Their lungs were turning to scar tissue. The US government had the data. The factories kept running anyway. Why? Start with regular copper. It's in every wire, pipe and circuit board on Earth. Excellent conductor, but mechanically it's soft. Under load, it deforms. You can't build precision springs from it. You can't use it anywhere. That mechanical stress and electrical performance have to coexist. Now add beryllium. Just 2%. That 2% changes everything. The metal becomes dramatically harder, comparable in strength to high-grade steel at peak hardness. But unlike steel, it still conducts, strong and conductive simultaneously. For most of the last century, no other standard engineering alloy came close to doing both at that level. Beryllium copper is non-sparking. When you strike most metals against a hard surface, you get sparks, tiny fragments of superheated metal. In most environments, it is not a problem, but in an environment containing natural gas, or petroleum vapor, or explosive dust, or ammunition, one spark is all it takes. That is why an oil rig worker reaching into a gas-rich environment uses a beryllium copper wrench instead of a steel one. That's why explosive ordnance disposal technicians handle certain components with beryllium copper instruments. That's why munitions facilities stock it as standard equipment. This is not a niche application. This is the material you use when the alternative is an explosion that kills everyone in the room. But the explosive environments are just the beginning. The same properties that make it the tool of choice on an oil rig have made it a default material at 35,000 feet. Precision connectors inside aircraft functioning under extreme vibration across hundreds of thousands of duty cycles without a single failure. It's in radar systems, scientific instruments. The spring contacts inside certain smartphones and laptops flexing and returning millions of times without losing contact pressure. NASA has used it, Boeing has used it, Lockheed Martin has used it, defense contractors who cannot name their programs have used it, and none of those systems care what it does to the people who make it. If you pick up a finished piece of beryllium copper, a wrench, a spring, a precision connector, it is almost certainly not dangerous. The beryllium atoms are locked inside a solid metal matrix. They are not going anywhere. You can carry it, use it, put it in your pocket. The finished product is safe. It's the making of it that kills you. When you machine beryllium copper, when you grind it, drill it, sand it, polish it, the process releases ultrafine dust. Particles so small you cannot see them individually with the naked eye. Those particles contain beryllium. Breathe them in, and your immune system marks beryllium as a threat. This is called sensitization. First exposure, you may feel nothing. You go home, you come back the next day. But something has changed, your immune system is now primed. And the next exposure, even a small one, can trigger a full inflammatory attack inside your lungs. Your body begins fighting itself. Granulomas form, nodules of inflamed tissue clustering around the beryllium particles. More exposure. More granulomas. The lung tissue scars progressively, permanently. The disease is called chronic beryllium disease. CBD. There is no cure, only management. Caught early, treatment can slow the progression. But the damage already done cannot be undone. Breathing becomes laboured, capacity decreases. In severe cases, respiratory failure. But here is the detail that made this so catastrophic for so long. The disease can take 10 or 20 years to appear. A worker breathes beryllium dust for 3 years, changes jobs, moves on, and then, a decade later, starts struggling to climb a flight of stairs. By the time they connect it to a factory they haven't thought about in years. Proving it is nearly impossible. The oil rig worker using the wrench was never at meaningful risk. The machinist, who spent 8 hours a day shaping that wrench, breathing air that looked perfectly clean, was being quietly destroyed. And this is where the story gets darker. Beryllium's history in the United States runs through the nuclear weapons program. They knew earlier than they admitted. The Manhattan Project used it. Post-war defense spending kept the processing plants growing, and the exposure standard first adopted by the Atomic Energy Commission in the late 1940s and formally codified by OSHA in 1971 was accepted by regulators without sufficient evidence that it actually protected anyone. Beryllium was not just an industrial material, it was a strategic asset. The same institution that needed it for nuclear weapons was helping decide how much of it workers could safely breathe. That conflict of interest had consequences. Cases of lung disease kept appearing. Misdiagnosed at first, the symptoms looked like tuberculosis. The connection to beryllium took years to establish. And while that argument played out, the factories ran. By the 1990s, studies showed workers were developing chronic beryllium disease even when their exposure levels were below the official safe limit. Not slightly below, well below. The disease was showing up in quality control staff, maintenance workers, people who worked in the same building and never touched the metal directly. The exposure limit was wrong, had been wrong for 50 years. Lawsuits followed. Manufacturers were accused of knowing about the risks earlier than they disclosed. Some cases settled for significant sums. It took until 2017 for OSHA to set a new limit, roughly 10 times more stringent than the old one. The International Agency for Research on Cancer had by then classified beryllium as a Group 1 carcinogen, but the plant doors stayed open. Not banned, not shut down, regulated more tightly, but even meaningful progress in well-run facilities has not closed the factories. The reason they stayed open is the part nobody wants to say out loud. The engineer's answer has, for most of beryllium copper's history, been blunt. Nothing else does everything it does. That answer is now more complicated, but it has not fully changed. What is at stake here is not a material that makes slightly better kitchen appliances. This is the wrench standing between an oil worker and a gas explosion, the spring contact keeping avionics alive at 35,000 feet, the connector that cannot degrade inside a weapons system. In those environments, almost as good is not a grade. It is a failure mode, and failure modes have body counts. So the alternatives get evaluated with brutal honesty. The traditional candidates, phosphor bronze, titanium, aluminum bronze, each solve part of the problem. Phosphor bronze is safer to manufacture, but significantly weaker and lower in conductivity. Titanium is extraordinarily strong, but barely conducts electricity. Aluminum bronze has worked as a genuine replacement for non-sparking hand tools in some settings. But in precision spring contacts and high-performance connectors, the traditional alternatives have historically fallen short. Here is where the story has started to shift. In recent years, a class of beryllium-free copper alloys, copper-nickel-tin spinodal alloys, commercially known as tough met or finadal, have emerged as credible alternatives in some of the most demanding applications. They offer high strength, good corrosion resistance, and no beryllium hazard in manufacturing. Aerospace companies, oil and gas operators, and defense contractors have begun qualifying them for applications that previously required beryllium copper. The substitution is real. It is happening, but it is incremental, not complete. While the engineers debate which alloy wins on a spec sheet, the machinists are still showing up to work. And the split tells you something important about where the real problem lives. In the oil and gas industry, the transition away from beryllium copper for non-sparking hand tools has been moving faster than almost anywhere else. The financial incentive is clear. Beryllium copper tools are expensive, liability exposure around worker health is significant, and aluminum, bronze and spinodal alloys have proven themselves to be adequate for the most common tool applications. On many modern platforms, the beryllium copper wrench we opened this video with has already been replaced. The tool that started this story is, in that specific application, increasingly a relic. But follow the same material into the electronics supply chain, and the picture changes completely. The precision spring contacts inside high-performance connectors, the components that carry electrical signals in aerospace avionics, in military communications equipment, in medical devices, are where beryllium copper's combination of conductivity, springback and fatigue resistance is hardest to match. Spinodal alloys are stronger in some respects, but their electrical conductivity lags. For a connector that has to flex millions of times while maintaining a reliable electrical signal under vibration, the kind used in aircraft instruments or satellite ground stations, that conductivity gap matters. Engineers who have tried to substitute have, in some cases, had to go back. That split, tools moving away and precision connectors holding on, reveals something the headlines about beryllium copper almost never capture. This isn't one story. It's dozens of parallel engineering decisions happening simultaneously across different industries, different applications, different risk tolerances. In some of those decisions, beryllium copper has already lost. In others, it will be the default material for another generation of products. And the workers making those products in the facilities that haven't switched, in the supply chains that still depend on it, are still being asked to accept a risk that the engineers specifying the material will never face themselves. If the safer material fails, the oil rig still explodes. Engineers do not get to choose between a dangerous option and a safe one. They are choosing between different kinds of dangerous. Beryllium copper's danger happens in a controlled factory with monitoring and protective equipment. The alternative's danger happens in a fireball. So industry has made a calculation and continues to make it, application by application, with tighter regulations, better ventilation, mandatory health screening and modern exposure controls. The risk to workers can be substantially reduced, not eliminated. Reduced. And reduced in the language of industrial risk management means acceptable. And so the material survives, dangerous to make, difficult to replace. Beryllium copper is not unique in this position, it is just unusually honest about it. It is not controversial because it failed, it is controversial because it worked too well. The same pattern runs through asbestos, lead paint and a longer list than most people realise. Materials that performed exactly as intended and then extracted the cost somewhere else from someone else. Years later, beryllium copper is still here. The industry called the remaining risk manageable. The word they used was acceptable. Acceptable. That word does a lot of work in industrial material science. The spring goes into a connector. The connector goes into an aircraft instrument panel. The aircraft carries 200 people safely across the ocean. Somewhere, a machinist who made that spring goes home with a cough they have been ignoring for 6 months. The question beryllium copper forces is not really about one metal. It is about every material we depend on that someone, somewhere, pays a price to make. Most of them we never think about. Most of them we do not know the name of. The factories are still running. The damage cannot be undone. And the people making the decisions have never breathed the dust.